Okay, so this is a video on the characteristics of exponential functions. So just a little introduction to Chapter 7, Section 7.1 in the book. And we're just going to look at some graphs and equations for exponential functions. So to start off with, we're looking at, in this one, it's a little bit small, but that says y equals 2 to the power x. So you can see that the variable is the exponent, so that's why this is an exponential function. And so we're just going to start with making a table of values for that. So 2, and we're starting off with x being -3. 2 to the power -3 is 1 over 2 cubed, which is 1/8. So our first y value when x is -3 is 1/8. 2 to the power -2 is 1 over 2 squared, which is 1/4. Okay, 1/4 here. -1, 1/2. By the same fashion there, right? 2 to the power 0. Anything to the power 0, 1. 2 to the power 1, 2 squared, 2 cubed. So if I just pick finer thickness of that pen, it might show up a little bit better in our graph. So here we're making a graph. We had 1/8 when x was -3, so that's way down here. 1/4, 1/2, 1, 2, 4, and then 3 was 8. This isn't the best graph, it's kind of blurry, but you get the idea that we have that shape. So when we talk about exponential growth, that's this here, right? You can see it's growing exponentially really fast. Domain and range, so x is an element of real numbers. X can be anything. And you can see that this is going upwards and to the right here, and then downwards and to the left. And it's getting ever closer to our x-axis, but never actually touching it. So y is greater than 0, and y is an element of real numbers. X and y intercepts, well, because y is always greater than 0, there are no x-intercepts. And the y-intercept is at 1. That's this point right here. And we'll see that anything to the power 0 is 1, so we're going to have that value there. The equation of the asymptote is y equals 0. That's the line it doesn't touch. And this is just simply the x-axis. Discrete or continuous, well, this is continuous. Discrete meaning made up of dots, right, with points missing and so on. But this is a continuous smooth curve that we've drawn. This is an increasing function. You can see that as I go from left to right along here, that the graph goes up, so it's increasing. All right. Then the next one that I wanted to look at is where the base is 1/2 instead of 2. So y is 1/2 to the power x, and x is -3 as our first point. So when x is -3, what happens? Well, remember that to make this a positive exponent, I do the reciprocal of the base, which is 2, to the power 3. Now it's positive, right, when I do the reciprocal, is 8. So here when x is -3, y is 8. 1/2 to the power -2 is going to be 2 to the power +2, which is 4. -1, well, that's just going to flip that 1/2, and it's going to be 2 to the power 1, right? So that's our value of y when x is -1 is 2. 1/2 to the power 0 is 1. And then 1/2 to the power 1, well, that's obviously just a half. 1/2 squared is 1 squared over 2 squared. 1/4. So you can see it's going to be the opposite behavior of this one here. So x is -3, y is 8, -2 and 4, -1, 2. There's that y-intercept at the same spot, and then it decreases down here. So we have this shape. Domain and range are the same. Oh, hold on. Do that again. Oops, there we go. It works this time. X is an element of the real numbers, and our range y is greater than 0. Again, no x-intercepts, and the y-intercept is at 1. Asymptote is the same place, y equals 0, which is our x-axis. Again, it is continuous, but this time, it's not an increasing function, it's a decreasing function. So a decreasing function we call decay, exponential decay, and an increasing function we call exponential growth. All right, next. I have a second example for you here, and in this one, what happens if the base changes? So we want to compare two functions, y equals 2 to the x and y equals 4 to the x. And then over here, 1/2 versus 1/4. So 2 to the x, well, we already did that one, and we know we have these points. 2 squared is 4, 2 cubed is 8, and we have 1/2 and 1/4 and 1/8 and so on. So we have this graph, that's this one. Maybe I'll just pick a different color to show you the other one, which is this guy, 4 to the x. So 4 to the power 0 is still going to be there at 1. But now 4 to the power 1 is way up here at 4, whereas this guy was only at 2. And 4 squared, well, I'm way up here now at 16. I'm off my graph even. So you're going to see that we have that kind of a shape for that guy. So when the base is larger, when the base is 4, it increases faster. All right, and that's what we can see here. This point is above that one, and the purpley graph is above the black one, so it's increasing faster. Over here, I compare y equals 1/2 x. Well, we just did that one, so we plot a couple of points for that guy. Here we go. It looks something like that. And then if we think about the 1/4, this guy, we're going to have that same point there, 1/4 to the power 0. But if you think of when x is -1, 1/4 to the power -1, that's 4. So when x is -1, this is y. So that's way up here. And 1/4 to the power -2, that's going to be 4 to the power +2, which is 16. So again, here at this point, I'm way up there somewhere off my scale. So we have something like that. So again, this one is decreasing faster when we have a smaller base. So smaller base is going to decrease quicker. All right. Now we're looking at some scenarios where we have exponential growth. So this is an increasing function. Those are synonyms. A bacterial culture is made up of 100 cells. And the number of cells doubles, so that means times it by 2, every 30 minutes. And let's fill in this table. So at time 0, we have 100 cells. And then after 30 minutes, we're going to have double that. And so that's one doubling time. After 60 minutes, I'm going to have double this amount, right? So take that and times it by 2. That's 400. We've had 2 doubling periods. Then I double this 400. I get 800 at the third time segment there, third time of 30 minutes. Double 800, that's 16, and so on. And so that would be 4 doubling periods. So what I would say is that the number of times the cells double is our time. So for example, 90 minutes, our time divided by 30 minutes, right? This was 90 minutes divided by 30, that gives me 3. Or this was 120 minutes divided by 30, the doubling time, which is 4. So in general, the number of times the cell double is the time in minutes divided by 30. Over here, I would say I started with 100 cells, and I times it by 2 a number of times, and I would make this my exponent, t over 30. And if I use this equation, this would tell me how many bacteria I would have at a particular time. So, and if you don't completely get where I got this from, so I had 100, and I times it by 2 to the power 0 when I had 0 doubling times, and then 100 times 2 to the power 1 because I had 1 doubling time. 100 times 2 squared. Well, 2 squared is 4 times 100 is 400, and that's what I have in this same row. So this is our exponential equation that models this bacterial culture's growth over time. So just time over 30. So on the next page, we've got a couple of questions. Write the equation B of T, so probably the number of bacteria over time, the number of cells, in T minutes. So that's just my equation from before. B of T is 100 times my base 2, and that makes sense that the base is 2 because the population is doubling, and then here time over 30. And now we're asked to use the equation to determine the number of cells after 2 hours and 7 minutes. So let's see, 2 hours times 60 minutes per hour means 120 minutes plus this 7. So 127 is our value for T, and that's going to go in here in our equation. So how many bacteria do we have when T is 127? Well, let's see. 100 times 2 to the power 127 over 30. And I would just pop that into my calculator and see what I get. And the answer is 1,880. So there you have it. All right. So the next question is an example of a decreasing function. So in this case, we're looking at a half-life of an element. So this is a common question for a decreasing function, right, which we call exponential decay. And maybe you've talked about this in chemistry. Half-life is the time required for half, so that's giving me the base of my function, right? To be converted into another element through a decomposition reaction. So an isotope of strontium, strontium-90, has a half-life of 25 years. So we're going to complete this table and see how much of this strontium-90 have we got after all of these halving periods, right? It's halved. So the number of half-lives at time 0 is 0. And then here, after 25 years, that's 1 half-life, I have half this amount, 10. So it's like I took that 20 milligrams and times it by a half. Down here, if I divide this by 2, I should have 5 milligrams, and that's 2 halving periods. So I started off with 20, and I times it by a half squared, right? That's the exponent here, the number of half-life. So a half squared is 1 over 4, and 20 times a quarter is 5. A quarter of 20 is 5. And then down here, 2.5. After 100, I only have 1.25 milligrams based on the original 20. That's 3 half-lives here. For this, I could use my equation, change the exponent to a 3. Here, change the exponent to a 4. And hopefully, you can see that the number of half-lives is the time. So whether it's 50 years, 75 years, or whatever, divided by 25. So in this case, 100 years divided by 25 is 4. And 75 divided by 25 is 3, and so on. So my equation is going to be 20 times 1/2, right? It's a half-life. So that makes sense, to the power t over 25. So it's very similar to what we had before, right? This is my starting amount, and the other one, it was 100 bacteria. This time it's 20 milligrams of this substance. Now, because it's a decreasing function, my base is a half, it's a fraction, and then there's my exponent, time over 25. So again, just a couple of questions. Write an equation. So Q of t is 20 milligrams times the half base, right? That's my base because it's a half-life, t over 25. And now they're giving us a time. After 120 years, so that means t is 120, what is Q? How much strontium remains? So the Q of 120 is 20 times 1/2 to the power 120 over 25. And if I do that equation in my calculator, right, enter this in your calculator, you should get 0.718 milligrams of that substance. So in general, an exponential growth or decay is written in this form. So we have y equals a times c to the power t over p. So a is the initial amount, c is the growth factor. So this is the base of the exponent, base of the power, sorry. So is it doubling or tripling? If it's doubling, the base is 2, right? So did it double? That means the base is 2. Is it a half-life? Then the base is a half, and so on. Okay. If the base is greater than 1, it's going to be a growth function, right? We're going to see that shape that we saw where it is an exponential growth. But if the base is between 0 and 1, in other words, if it's a fraction or a decimal between 0 and 1, it's going to be the opposite shape. It's going to be that exponential decay. T is the total time, and P is the time required for growth or decay. So in our decay example, the value of P was 25 years. And for growth, what was it, 30 minutes, I think, was the amount of time for it to double. So you're looking for that in your question to be able to answer it. Okay, so at the end here, I have another question for you to give this a try. Maybe pause the video here and try this one.